Hello everyone, good evening. I'm Anish Ambekar, PMRF and PhD candidate from Aerospace Engineering IISc Bengaluru. Welcome to this week's live interaction for the NPTEL lecture for the NPTEL course Dynamic Behavior of Materials. The course code is NOC 24ME102 and this session is dedicated to the content covered in week 11. The outline for this session follows basically the week 11 contents, which are uh, dislocation dynamics, physically based constitutive laws, shockwave strengthening, dislocation generation. So, dislocation dynamics. If you recall from the last week's lectures, we ended on how there are different regions inside. Uh, in the case of metals, there are different regions where dislocation velocity depends on the resolved shear stress. So, if I were to draw that schematic diagram, the three regions. On y-axis, we have a dislocation velocity. On x-axis, we have your result shear stress. There are roughly three regions in this domain. So, this is actually a log-log plot. This is the region 1, region 2, and region 3. And all these three regions have three different mechanisms. So, we'll go through them one by one. Region 1, it is also, it will be called as thermally activated dislocation motion. The reason one is relates to thermal activation. And what do we mean by that? Suppose we take the case of a edge dislocation. If we apply a shear stress on its boundaries, what do we see? We'll see a pulse Navarro barrier in terms of force required to overcome this further dislocation to make a jump to the next unit cell. So the pulse Navarro barrier will be a can be represented roughly by the sinusoid with period of A naught being lattice parameter. So it's the pulse Navarro Navarro force that is required to be overcome before dislocation starts moving. So specifically, it refers to the peak of that resistance that we see. And one more important thing, it is an in-plane resistance. Another type of barrier encountered is an out-of-plane resistance in the form of forest dislocation. So suppose this is the dislocation moving along this drawn slip plane. So perpendicular to the slip plane, you may have this forest dislocation. So this is my primary slip plane. Forest dislocation. Forest dislocation provides an out-of-plane resistance. Which of these resistances is dominant depends on the type of, sorry, on the lattice structure of the chosen material. This is out of forest dislocation, out of plane resistance. And if one were to plot how the resistive force varies with difference, one may end up with a plot that looks like this. Force versus distance plot. And you have a few short range barriers, something like this. So this is a short range barrier, and it depends on the it depends basically on your it's basically one of these two types. So how the dislocation would move forward from one unit cell to next. Whereas if you have a larger distance being covered, then you have a long range barrier. Long range barrier is typically a function of the structure, and as you can very well, as we'll see quickly, the short range barrier depends on the surrounding temperatures. So what exactly is so temperature corresponds to a thermal energy, and what exactly is it? So from an atomistic perspective, thermal energy refers to the basically an increase in temperature leads to an increase in thermal energy, which leads to an increase in the amplitude of vibration of atoms. So, an increase in, we already seen that this frequency is very something like 3 into 10 to the power 13 hertz. So like I think that's 30 terahertz. Okay, so this is the thermal. This is when we talk about, say, the energy required to overcome a barrier. We can draw a free body diagram. Sorry, we can draw a force displacement plot. The area of this force displacement plot would refer to energy. So I'll just mark out a few points. Right. So what do we have here is, so this is the peak barrier. So peak force or the barrier required to be overcome when we want dislocation motion, and this is the free energy contribution corresponding to surrounding temperature. So as you suppose you have four temperatures, T0, T1, T2, T3 are the four temperatures. Should write temperature. Then as the temperature increases, the associated Gibbs free energy increases. So you have delta G0 less than delta G1 less than delta G2 less than delta G3. Increase in temperature leads to an increase in Gibbs free energy, which in turn leads to an decrease in the energy barrier. So the shaded part that I have shown is suppose for the temperature T1. So delta G1 is the shaded part in the left hand side plot, and what we see is the total amount of energy that we require to cross the barrier has gone down by the amount equal to the area enclosed in the shaded part, which means that because the energy barrier has effectively decreased, our dislocation motion has become easier, which implies dislocation motion easier as temperature increases. And if one were to plot the force, one were plot to for the peak stress required as a function of temperature, then one would find a plot that roughly looks like this. So it's a decrease, it's not exactly an exponent, it's a decreasing plot, tau 0, tau 1, tau 2, and tau 3. They correspond to temperatures T0, T1, T2, and T3. So while thermal energy plays a role, so it's important to note that thermal energy plays a role in short range barrier, short range obstacle, uh, but not in long range obstacle. So we can write the flow stress to be any given point to be sigma is equal to sigma g, which refers to the athermal barrier. It's a structural property. It's a, not property. It depends on the structure. Rather, it's a function of structure. Sigma star, temperature, strain, rate, and structure. This is athermal barrier. It depends on long range obstacles. So the short range obstacle, suppose if you consider the pulse Navarro case. In the pulse Navarro case, when we have to move the edge dislocation from one by a step size of one unit cell, then you need some amount of energy to overcome that energy barrier. As the temperature increases, you can expect, because the atom vibration amplitudes increase, you expect that the dislocation will be able to move much easier ahead, which basically means that your stress or force required due to the thermal component has decreased. So the thermally activated, that's why it's called thermally activated. Uh, Basically, it becomes easier as temperature increases. And one more thing we are interested in is looking at strain rates, function of strain rates. So we'll delve a bit into statistical mechanics. So the probability of equilibrium fluctuation in energy of a system greater than delta G as per statistical mechanics is given by Pb is equal to exponent of minus delta G by Kt. K being the Boltzmann constant, T being the temperature in absolute units. So what we are saying by this statement is that as delta G increases, as the value delta G increases, the probability that the system will exist in that state exponentially decreases. Similarly, as the temperature T increases, for a fixed delta G, you can imagine that the probability will end up increasing. So, which means that system will occupy higher and higher energy states. So, this probability is useful in the way another way that your probability that a dislocation jumps successfully over a short short range obstacle is basically the number of V1 by V naught is number of successful attempts. We can write it per unit time, so that basically makes it frequency upon number of total attempts. SPB, which is exponent of minus delta G by KT, which means number of successful attempts is equal to nu naught. Frequency of successful attempts is equal to nu naught minus delta G by KT. Nu naught is usually a couple of magnitudes smaller than the atomic frequency uh, lattice vibration. So it's of the order of 100 gigahertz, if I recall it correctly. One more expression is epsilon dot, which is delta epsilon by delta t. Delta epsilon we can write as 1 over m, which is the orientation factor, rho b delta l into 1 by delta t. And 1 by delta t we can write as exponent nu naught exponential of minus delta g by kt. This is basically this is the this is the average distance between obstacles. So we have written it in terms of the dislocation density rho, orientation factor, and b being the Burgers vector. And delta t refers to average time to jump obstacles. So which makes 1 by delta t to be nu naught exponent of minus delta g by t. So you can write epsilon dot is equal to rho b delta l nu naught by m into exponent of minus delta g by kt. Taking the left hand side bracket and writing it as epsilon dot 0, you end up with epsilon dot 0 into exponent of minus delta g by kt. Juggling the terms around, you basically get delta g is equal to kt ln of epsilon dot naught by epsilon dot. So which tells us that delta g increases with temperature and delta G decreases with epsilon dot. So if I were to plot a stress versus temperature plot, note that there will be a long-term obstacle associated, a thermal component, which is sigma G, and the rest of it is sigma star. This is from our previous thing. So you have something that goes like this and ends up here. What happens is, as you have epsilon dot increases, delta G decreases, which means that the peak stress that is required for a higher strain rate loading, it's higher. This is how it looks like. So this is with increasing epsilon dot. So this covers the first region. The second region is called as drag, viscous drag, and it's similar to how the name sounds. So in fluid mechanics, we have already studied how when the object moves related, how if you have an object which is moving relative to the fluid, or if different fluid layers are moving relative to each other, a viscosity is present, which tries to sort of friction, which tries to dissipate energy. So we have velocity of dislocation, which is v, proportional to applied stress tau. So dislocation motion leads to temperature increase. What we have is energy spent on the system is basically can be split, say, 10% on dislocation motion, and about 90% of that goes into is basically dissipated by viscous forces. Right. So equilibrium is reached, and you have two forces, which is the applied stress tau into B Burgess factor, calling B into B being the drag coefficient, and V being the velocity. So you have using epsilon dot equal to 1 by m rho gamma dot, which is 1 by m rho BV, you end up with, you continue writing it up here, you end up with tau B is equal to capital B into m into epsilon dot by rho B. Assuming that the applied loading is assuming uniaxial stress as the applied load, you have using Morse circle, we get tau is equal to sigma by 2, that is the maximum shear stress. So we end up having sigma is equal to 2 beta m by rho b epsilon dot. So this is flow stress at given epsilon dot. So this is the drag mechanism as mentioned. It is not thermally activated, and it's depends on interaction of dislocations. So depends on interaction of dislocation. It can be of two types. First one being with thermal vibrations. So this is basically your phonon drag, and the other one is with electrons. This is your electron drag. So if one were to plot how the drag coefficient looks as a function of temperature, yes, this is 10,000. You would have something that looks like this is electron drag theory. This is uh, this is phonon viscosity, phonon drag, and this is experiment. The experiment was done by Parameswaran and Wiltman on aluminium. So here you can see that as temperature increases, the electron drag component decreases, which means they're not very easily moving around as much as they would at low temperatures. And that no longer causes as great of resistance to the dislocation motion. Other part is the phonon drag. Again, as the atoms vibrate more and more, with increases in temperatures, they'll interfere with dislocation motion. So beyond a certain temperature, they'll start dragging it. They'll they'll interfere with it and basically result in some sort of drag, so to speak. The final part in this thing is the third region, where you have relativistic effects. So, an interesting thing that has been observed is that if you plot the total energy of dislocation as a function of dislocation velocity by shear speed, so what we see is it's a very slow increase and then suddenly very sharp increase. So the total energy of the dislocation ut tends to infinity as dislocation velocity v approaches shear speed velocity. This ut is basically a potential energy plus kinetic energy at zero dislocation velocity. Ut is u naught as v increases, dislocation velocity v increases. Ut, sorry, the effective mass of dislocation increases. So it follows a relation similar to that of Einstein's relativistic theory. So 1 minus v by cs whole square. So in here, uh, there are a few things. Firstly, if we consider only the case of screw dislocation, only shear stress generated, and which means it cannot move faster than shear wave velocity. However, there are, I think, in SLB proposed something called a supersonic dislocation. And suppose you have an edge dislocation, you could have a combination of both dilatation and shear. So in that case, you can have something happening, but it's important to note here that experimentally we have not observed dislocation velocity to exceed the shear speed velocity. So one more important point is that the dislocation acceleration is very high. The dislocation acceleration is very high, which means that negligible time and distance required to reach steady state velocity. What do I mean by negligible time and distance? So negligible distance would be basically something that is angstrom or sub angstrom length, because the lattice parameters are itself in the range of order of say 1 angstrom or up to nanometer. You could have, what we are saying is that even before the dislocation has moved an entire only a single unit cell, that it would have already achieved its steady state velocity. So if we combine all these three regions, we end up with a plot of dislocation velocity. This is, you can think of this as a synopsis. shear speed, the stress, this is the linear line. So you could have sigma g, which is the athermal stress component. It's constant for a while. Then you have thermal activation, then drag, and then relative stability. This is region 1, region 2, this is region 3. So I am approaching the asymptote but not getting there quite. Okay, this covers dislocation dynamics. The next part is on physics based constitutive models. So far we have looked at how the dislocations may move. Now what we are interested in understanding is when they encounter a barrier, how they overcome it, what sort of but what sort of microstructural conditions dictate our material response at macro scale. So if we want to see the material response at high strain rate, it, as you mentioned, it depends on microstructure evolution. So microstructure contains defects, cracks, phase transformation. And at high strain rates, there are other considerations that become important. Specifically, you may have lattice rotations, you may have textures, which also play an important role. Suppose we consider material response at ambient temperature. It passes through different stages as we keep on increasing our strain rate. So you may have something like a power law creep at very low strain rates. Then it may move It may be replaced by obstacle controlled plasticity as the dominant mechanism, and then it in turn may be replaced by adiabatic shear, which we'll discuss in next week's lecture. And you may have something like a phonon drag. So this is with increasing gamma dot. So if I look for a single dislocation, suppose it goes like this. The bottom part that I'm just making bold now is the initial location of the dislocation, and then the top part is the final position. So the bottom part, so the top part is the final position, the bottom part is the initial position. This length we can call it L star, and the size of the barrier we can call it as lambda. So the physical process of overcoming barrier, the dislocation, overcoming the barrier can be thought of as can be thought of in terms of a stress versus distance plot. You have stress versus distance. There is an athermal component based on long range obstacle. We have a short range obstacle. We also have other shapes such as like a hyperbolic or sinusoid. This you'll have another short range barrier after a while and so on. This distance between the two short range barriers is L, whereas the width of the barrier itself is lambda. This L star. You can see it from the diagram on the left what we are referring. So your L star at low temperature, sorry, L star, which is the short range barrier periodicity at low strain rates. It is different for FCC metals and BCC metals. For FCC metals, the short range barrier is basically a dislocation forest. And your L star depends on dislocation density, your forest dislocation density, which in turn, this dislocation density increases with strain hardening. The other type is BCC metals. Here, the predominant mechanism for predominant short range obstacle is your Pulse-Navarro stress, which means L star equals A naught, which makes it independent of plastic strain. So, for FCC metals, the length L star, which is the periodicity of the short range barrier, it depends on the forest dislocation density. Whereas for Pulse-Navarro, for BCC metals, the predominant short range obstacle is the Pulse-Navarro stress, which by its definition we have already seen in the very first slide that it is equal to the lattice parameter. So as a result, you have two different underlying mechanisms which inform two different behavior. This was taken into account by the Cherry Armstrong ZA model, who proposed so ZA model is microstructurally based constitutive relation, and it matches well with experiment. And it is generally calibrated using Taylor's test. We have seen like short cylinder fired at a velocity and rigidly impacting a rigid wall. So and it makes use of thermally activated dislocation motion. So as we mentioned, so you have the different forms for strains and strain rates for the L star. And Cherry Armstrong also observed that BCC metals show higher sensitivity to both temperature and strain rate than FCC metals. So you for the FCC metals, ZA model looks like sigma is a thermal component, C2 root epsilon. Why this root epsilon? We'll get in a moment. Exponent of minus C3 temperature, C for ln of epsilon plus A root T. And for BCC metals, you have the flow stresses summation of A thermal stress plus C1 exponent of minus C3T plus C4T ln of epsilon dot plus K root T C5 epsilon dot. So let us look at both of them. So the very first term in both is your A thermal stress. Then there is an exponent term combining temperature and strain rate. So this is your temperature and strain rate dependence. This K root D is basically a Hall pitch law. It's quite well known, where D refers to the diameter of the grain. Epsilon restaurant makes it work hardening. So BCC metals, as we discussed in previous slide, will have a work hardening due to forest dislocation, short range being the dominant short range obstacle. What happens for FCC metals is that there is this activation area A is equal to L star into lambda. So it depends on this depends on epsilon for FCC, but not for BCC. This is because that the spacing L star for the forest dislocation, which is the predominant short range obstacle for FCC metals, that spacing decreases as the forest dislocation density increases. So there is a inverse relation between for FCC, uh, you have something like rho 1 by L star square. So which means that as the applied strain increases and they come closer and closer together, your strain will again play a role, which is why that root of epsilon appears in the ZA model for FCC metals. And one more important thing is that there is a temperature rise during plastic deformation. So at low strain rates, you have an isothermal process. Things are allowed to cool down. Whereas at high strain rates, the changes are much quicker. So uh, there is not much time, not much area, sorry, volume or time for heat to spread, which means it does not reach an thermal equilibrium with its surrounding environment. So there is this quantity called as thermal diffusion distance, and it can be thought of as distance that the heat travels, the amount of distance that the heat can travel, and it's given by this formula D is equal to twice of root alpha T. So uh, suppose suppose you have epsilon dot of the order of, suppose epsilon equal to zero point 0.5, alpha equals 1.14 centimeter square per second, which is for copper. Then at epsilon dot equal to 10 to the power minus 4 second inverse, you have that we have T is equal to epsilon by epsilon dot, and which means D is roughly 150 centimeter. So very large amount of area for the this to spread. But if epsilon dot is equal to 10 cube second inverse, your D shrinks down to 1.5 mm. So as epsilon dot increases, you have an isothermal to adiabatic process change, thermodynamically speaking. And in this case, about 90% of work dissipated into heat, which means that rho Cp delta T is Beta is basically zero point 0.9 here, 90% into sigma d epsilon, epsilon, which means delta T is beta by rho Cp into strain energy density. So what we mean here is in this temperature rise section is that for low strain rate, you can imagine that there is sufficient amount of time and space for any heat that is generated to be spread out throughout the material so that the material reaches equilibrium with its surrounding temperatures. As the strain rate increases, material doesn't get as much of a chance, making the heat much more localized, and therefore it does not therefore you can think from a local perspective, from a local thermodynamic perspective rather, that the process for the low strain rate looks pretty much like an isothermal process, whereas the process for a high strain rate loading looks much similar to an adiabatic process. Here, about say a fraction of the energy, a large fraction of the energy rather, say something like 90% of the energy is basically converted into heat. So, if you, in case of plastic deformation at higher strain rate, so we can simply use our, we can figure out the amount of energy involved in strain energy per unit volume, and then from that we can figure out what is the temperature rise by making use of non-material constants such as density and specific heat. So I think next is on the next part is on the shockwave strengthening. So what do we mean here is, as the word suggests, as a shockwave passes through a material, it causes microstructural changes. So shockwave, I'll be using SHW for short. It leads to hardening of the material, usually with negligible strain, and it depends on both pressure and the amplitude of the pressure as well as the pulse duration. And this work hardening is seen in most metals, and it is there is usually a large number of effects generation. So if we see the hardening versus square root of pressure, the plot would look something like this for SS304, something like this for nickel. Another plot we can think of is hardening versus pulse duration. So increases and then becomes constant, increases and becomes constant. This is delta T. So I think this is for Inconel, 25 GPa, 15 micron, and nickel, 25 GPa, 25 micron. If we compare shock wave and rolling hardening, we see some interesting results. So I'm plotting Vickers hardness on the y-axis, and I'm plotting temperature on the x-axis. Suppose this is like the initial Vickers hardness, and this is for the nickel manganese steel. So as rolling increases, you have this 20% roll, This is a 40% roll. But with shock wave, you can have something like this shock wave at 33 GPa, and this one is shock wave at 16 GPa. So from this plot, we see that. So we'll go through. From this plot, we see that with rolling, you have an increase in hardness that seems to stay pretty much constant. With shock wave, you have a much larger increase in hardness, but as the temperature rises, that hardness drops off. So shock wave hardening, as we mentioned, there are both delta T and delta P effects. Winning is involved and pressure effects. This is due to dislocation generation. Shock wave hardening reaches a saturation level, and decreases for further increase in pressure. This is due to shock-induced recovery and recrystallization. So you have some alloys that look like, here I have shock wave pressure. So you could have an ultimate tensile strength like this and a yield stress that goes like this. So for some alloys with brittle phases, shock waves lead to breakage of the said brittle phase. So you could have an alloy with, as we have already seen, I think in week 4 or week 5, where you have different types of, where we looked at two different types of alloys, whether it's homogeneously distributed elements or if you have different phases inside the alloy. So if one of those phases is, so, say, brittle, then as the shock wave passes through, you could have a case where the brittle phase fractures out or shatters. What happens is this basically leads to micro cracks, which in turn results in failure. So here on the left hand side I have a plot for titanium alloy RMI 38644. This is 75 and 50 to 25 all in GP shock wave test. So there is an early reduction in strength. This is because initial martensitic phase subjected to reverse transformation, whereas at higher pressure you have dislocation strength overcomes this weakening effect due to reverse transformation. So the strengthening mechanisms are of different types. We'll be looking at one of those. So you have got strengthening due to shock wave. It can be classified like different types of dislocation, generation. Then you could have point defect, generation, deformation tuner. Right. So dislocation generation depends on both shock wave and the material. Specifically for shock wave, it depends on pressure and pulse duration. As pressure increases, dislocation density increases. Specifically, dislocation density is proportional to square root of the shock wave pressure, and this is up to a certain saturation value, after which shock wave induced heating will start to dominate. Then, as with temperature, as delta T increases, more time for reorganization. Sorry, more time for rather dislocation reorganization, which means cell walls are more defined. So you can have like two cells like this. You have a high density cell, high dislocation density cell, and a low dislocation density cell. So they start surrounding each other. This is more visible in optical micrographs. It's difficult to show that here, but I think if you can look at the textbook or on some online resources, it might be a good help. Dislocation generation, if we say it can happen due to shock wave, it can also happen due to uh, some other conventional deformation. So by conventional deformation, we mean causastatic or fatigue, and so on. Difference in both processes. That FCC metals, stacking fault energy determines dislocation structure in both shock wave and conventional or quasi-static loading. Whereas for BCC metals, dislocation more uniform in shock wave. A, a picture of how the stacking fault energy looks like can be drawn here. So stacking fault energy on the y-axis, you have critical twinning pressure. So roughly a straight line like this. At low stacking fault energies, Below critical tuning pressure, stacking faults are dominant, and beyond the boundary, you have twin faults which are dominant. And as stacking fault energy increases on the upper side of the below the critical twinning pressure, you end up having dislocation cells. You already saw those, so you have a low density and a high density region. So a high density dislocation region surrounding a low density dislocation. And when at higher for higher stacking faults and higher when pressures exceed critical twinning pressure, you end up with your mechanical twins. So you have got copper, nickel, aluminum somewhere on this plot. So there you see either the dislocation cells or copper depending on critical twin. Sorry, depending on whether the pressure is above or below the critical twin. So as stacking fault energy increases, things pretty easily understandable. Your critical twin pressure also increases. And this above plot is the defect structure in FCC. And there are different ways to model dislocation generation. One of the most, one of the more popular ways is using a homogeneous dislocation generation theory model, which was proposed by Myers, has certain key advantages over its over the models before it. Particularly, it takes this following axioms that dislocations are homogeneously generated at shock front by deviatory stress. So that nucleation of dislocation ends up relaxing deviatory stresses involved. As dislocations, they usually move at a short distance for a short distance at subsonic speeds, and any new dislocation interfaces they generate as more and more dislocation faces generate as the shock wave propagates forward. So one of the advantages of this homogeneous dislocation generation model proposed by Myers is that it does not require any supersonic dislocations, and it ends up actually getting us an estimate for dislocation density. So I'll just write down the names. This dislocation, homogeneous dislocation generation by Myers. And here you have doesn't require any supersonic dislocations and predicts residual dislocation density. Okay, so that covers what we had for this session. Thank you for watching this online or on YouTube, and I'll see you again on the next one.